Welcome to a new video. In this video we will discuss the Square-Wave Oscillator. We will see first the derivation of the oscillation frequency. We will also discuss about the positive feedback, the principles of oscillation, and we will do design example to calculate the component values. Of course we will see everything step by step in our calculations and so verify this in T90i SPICE simulations. Okay, first about the operation principle. We'll talk about the positive feedback that is necessary to have an oscillation. So we have here the general positive feedback configuration of an op-amp. You see here the op-amp and triangle symbol. You see here the positive feedback configuration. You see a part of that output using positive feedback will be then at this non-inverting input. This can be pictorially also shown here. So we have sort of a level, which is then this ball. And at that point, I'm approaching this, let's say, maximum point. But a small change to the left or a small change to the right will create now that this ball can fall down that way or that way. This is sort of an unstable situation, but we have still two stable states. That's also what we call a bistable operation. So we can say in general an amplifier and positive feedback with a loop gain larger than 1 that is necessary can become unstable in general. But we can create what we call quasi-stable operation if we limit the output to certain values. If there is a resistor voltage divider as shown here in a positive feedback, that will then establish some voltage at this node depending on the voltage of the output. So if the voltage is, let's say, the maximum, then you get a part of it here at this node by using here the voltage divider rule. If this is the minimum, then you get again another threshold at this node. So we have then two threshold voltages depending on the output voltage. If the output has only two extreme states, then we can have now bistable operation. Now we have this way or that way. That's also what we call the bistable state. So we have now two states, one left, one right, and these are the bistable states, which is in theory not unstable. It is bistable. So only two states creates a stable situation. Now the circuit characteristics can be discussed using this circuit, for example. We have this input voltage at the inverting input. Again, the same positive feedback. Now this node of the op-amp and this node of the op-amp will be compared by this op-amp. If the non-inverting is larger than the inverting input, the op-amp output voltage will then go to its maximum possible output voltage. In the reverse case, that means inverting input voltage larger than the non-inverting input, then this goes to the smallest value, the most negative output voltage. But it can be that, of course, the op-amp in practical cases consumes some voltage, so that will be then less than what you supply for your operation amplifier. So in the first case, let's say that we have the VI over V out characteristic as shown here. So we can say that our input voltage starts at some negative value and is increasing actually. That is this blue line, and then at that moment the output voltage is at this high state. Why? Because this is a lot smaller than that one, so the op-amp is clamped to its maximum possible value, which is then V max. At some point we approach here a value which is larger than this value, which is then this voltage, because there is some voltage here, let's say 15 volts, and by this voltage division, let's say we have here 4 volts, just an example. And if I approach here 4 volts and larger than 4 volts, that means I have a threshold here. Then I go down because this is now larger than that one. And the op-amp creates now a clamping to the most negative output voltage, which is then V minimum. But it can be also that I go back. So I can also go back with my input voltage. So I make it smaller, 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 and then make it negative. At some point, this is less than that one. So because since this has clamped in this case all the way to the negative supply, I mean the output voltage, then this is, let's say, minus 15 and this is now minus 4 volts. So in order to switch again back to the positive side of the output voltage, I need to go down lower than a minus 4. So there is a threshold high and threshold low. So it is not triggering at the same voltage level. Now if I go back and then I have then this relationship, so we can also combine these two graphs together and create here this nice VI over V out characteristics. And what we see here is that, again, as said before, threshold high and threshold low, so you don't trigger at the same voltage, so you actually have created a higher threshold voltage given by this expression which is then just this voltage divider, R1 over R1 plus R2 times the Vmax. And we have also the lower threshold voltage, which is then given by this using this minimum. And this is also called here two nodes. We will call here the hysteresis. So we have a safety region, which is very important in order to not have multiple triggering by some noise or interference. Let's see about this hysteresis in more detail in this next discussion. For instance, we have a comparator not having a hysteresis. Then this circuit is then shown here, very general. We have this input voltage, there's a reference voltage, we compare with this input voltage, and there is an output. For example, if I have a blue line here, which is then our signal at the input, which is of course not what we wanted, but due to noise or interference, this is what we have. And I have set, or we have set our reference at this line. So this is our reference voltage. What happens with the output voltage? The output voltage is now triggered here, again getting back because of this interference, and then triggered here again back, triggered here, again back, triggered. So there are some multiple triggerings, unintended triggerings, because of this noisy or interference coupling in this information signal, which is not what we want. So noise added to the input signal can cause unwanted transitions in the output signal. So how do we solve this? Now, we can use the Schmitt trigger circuit. It's called the Schmitt trigger, which has this hysteresis, which is sort of a safety region where you actually want to trigger, but you go a little bit up and a little bit down, and you create two threshold voltages instead of one reference voltage. And now we can create here the Schmitt trigger circuit having a hysteresis. In this case, the input here, this node voltage, always compared to this ground voltage, which is then 0 volts. Now we have here, for example, some noisy or some signal which is corrupted by interference or noise. And then we have the 0 line here, which is then the reference, because this is then the reference signal. And now there are two states, which is then the threshold high and threshold low, which is then used as triggering instead of just one as we have it here. And this is a more clean way of triggering instead of that one. That's also what we will use in our oscillator, which is then the Square-Wave Oscillator. And this is now the hysteresis and the characteristics between the input voltage and the output voltage. You see actually that when the threshold voltage is high is approaching, this goes to the higher state, and when this is now approaching, this goes actually down. Okay, let's go now to the situation where we talk about the bistable multivibrator circuit, where we have an RC element in it. This is what we have discussed, where we see the V out, V in and V out characteristics. So in this case, this is the V in, this is the V out, and then we will loop it back to our capacitor, and that will then charge, discharge, charge, discharge, and create by this change this square wave output voltage. So the circuit then will be like so. So we have here our op-amp again in the positive feedback configuration with these two resistors R1 and R2, and by changing the output to high or low state, we can charge or discharge our capacitor through this resistor. And that is the effect of this, where you see the graph. So now we have here the output, and we have here our capacitor voltage, which is then this voltage here. And the ratio here, what we call beta of this node voltage, is then R1 over R1 plus R2. That is the voltage, the fraction of the voltage which we have from the output at this node, which is called the non-inverting input. Okay, in this case, the higher threshold voltage is then given again by this expression, and the lower threshold voltage is given by this expression. Okay, let's see how we can determine now the expression for the oscillation frequency for this circuit. We consider the op-amp to be ideal in the first sense, so let's see how we can discuss this. The output levels of this circuit depends on the op-amp you're using. If you consider it to be an ideal, so perfectly ideal op-amp, then you have what you put here as the power supply is also, the maximum will be at the output and the minimum will be also at the output. So the Vmax is then a VCC, which is then called the positive supply of the op-amp, and the V minimum is then a VEE, which is the negative supply of your op-amp. Again, in practice, this can be 1 or 2 volts smaller than what is given here in the power supply. The time constant in our circuit is then given by the RC, so it is then the tau is equal to the product of this resistor and the capacitor. That is important. And we have our feedback ratio, which we call the beta, which is then R1 over R1 plus R2. That is shown here. The threshold voltages for this circuit are given by these two expressions, the higher threshold voltage and the lower threshold voltage. Again, looking at the output voltage maximum and the output voltage minimum by, again, the same beta. So you can also call beta times V max and beta times V minimum for the threshold high and threshold low. Okay, let's designate this V plus node and V minus node. So we will now do the analysis in more detail, because we need to have the oscillation frequency, and for that we need to have the period of the oscillation. So we have a charging of this capacitor and discharging of the capacitor. So we will divide the problem in two parts, where we discuss first the charging time, which is called now here Tc, and we will do next the Td, which is then the discharging time. So we can see here now the graph in detail for our output, the charging of the capacitor and discharging, and also the voltage waveform at this node. This waveform is because there are two states for the output. So there is maximum or the minimum. For this blue graph, that is actually part of this output voltage, which is then here because of this voltage division by this feedback ratio beta. So that's why we have here a smaller amplitude than here. And this charging and the discharging is because of this time constant in this capacitor and the resistor combination. And we have now here that this is going to the some level. It is approaching actually the Vmax, but it is then again clamped down, because then we have changed again our threshold voltage to a different value. Again, it will then discharge going to the V minimum, and then you get this charging, discharging, charging, discharging curve and create this output voltage. Now, general step response of a first order RC circuit can be then used to set up the equation here. And that's shown here. So the capacitor voltage here, this voltage, is given by this expression where you see the final value, which is actually approaching to that one. The initial value, which is then this, beta times V minimum, because it's starting there. And then minus the final value times the e to the power minus t over tau. So you see actually here three parameters, time constant, the final value, and the initial value. Now we know the final value is shown here, so because it is at this node, we can see that after Tc seconds, so from 0 to Tc, if you consider this 0, our signal, our voltage will be then beta times V max. So we can substitute that in this expression, and then also have substitute for Tc. And then you have this expression. Now we can now rewrite this, so place this V max to the left side, and you have this expression. Then you have now the expression here. Now you have e to the power minus Tc over tau is this ratio. Now we can now take the inverse of this exponential, which is then the minus Tc over tau will be then ln of this ratio. Now we can now multiply the left and the right hand side by this tau. So we go step by step to our charging time expression. And now we have here the minus Tc. I want to get rid of this minus. I can do that by multiplying the left side and the right hand side by minus 1. If I do that, I can also flip this fraction, which is the characteristic of the ln, so which is an identity in the ln. So we can now have the beta times V minimum minus V max over this, which is actually shown here. What you also see here is that we can divide here the numerator and denominator by V max. Then we have here this, which is shown here, minus 1, and then we have here beta minus 1, which is easily readable. Now we have our charging time expression in terms of the beta, the two output levels, V minimum and V maximum, and also of course the time constant tau. But we know for symmetric output states that the V maximum is the minus the V minimum. So if it is plus 10, the other one will be minus 10. That means this ratio is minus 1. So we can say this is actually minus beta, so beta times minus 1. And now we can also rewrite this. So if I now multiply this by minus 1 and this by minus 1, I can do that mathematically, no problem. Then I have this expression, which is then the charging time is tau times the ln of 1 plus beta over 1 minus beta. So if I change the beta, I can change the charging time. Okay, now we have the charging time expression. Now we do again the same process for the discharging time, which is then this part of the curve in this pink graph. Now we can again set an expression for the discharge time using the RC step response expression. We have again the capacitor voltage, which is then equal to the final value. Now the final value here for discharge is the low state of our output, so it will be V minimum. And then in parentheses the initial value, which is then beta times V max, minus again the final value, and then again e to the power minus t over tau. So again 3 parameters: initial value, final value, and the time constant. Now we know again our voltage of the capacitor will be at the value here at TD, so at TD seconds later it will approach beta times V minimum. And that is the situation where we can use here in order to get the discharge time, which is then the TD. So we substitute here the beta times V minimum, also from the graph you see that. This is then written like so, so you see here specifically the TD. And now we can replace this V minimum to the left side, similar to what we have done for the charging time analysis. Now we can now do the expression such that we have the e to the power minus td over tau eliminated. So we have actually now this, which is the left side over this fraction. You see here actually now the expression. Now we can do again the same thing. We take the ln of the left and the right hand side. So you have this fraction minus td over tau is equal to ln of this fraction or this ratio, again times the tau. And now I want to get rid of this minus sign for the td. So I will do -1 left side times -1 right side. That is the identity of the ln again. So this ratio will flip. And I have now this expression. Now what do we next? We can now say that we can divide again by V minimum here, because then this will be beta minus 1, the denominator in the fraction. And this will be beta times V max over V minimum minus 1. But we have discussed this also with a charging time analysis, that the V max is equal to minus V minimum. That means this is then effectively -1, this ratio. So it will be then -1 times beta will be here minus beta minus 1 over beta minus 1. Again, we can put this in a nicer form by multiplying the numerator and denominator by -1, and you have this expression. Now what do you see? The charging time and the discharging time are exactly equal to each other. Okay, now our purpose was also determining these two charging and discharging parts separately. We have it now. Now we can go to the total part, which is the total period, capital letter T, which is a summation of the TC and TT. That's shown here. That means just this plus that, which is effectively 2 times that. That is actually shown here. Okay, now we can also substitute the beta, which is our feedback ratio, given here R1 over R1 plus R2 in this expression. So we can now clearly express our charging, the total period, in terms of the resistors and the capacitors in our circuit. Now let's do that. That is now R1 over R1 plus R2, also in the denominator. Now we can multiply the numerator and denominator by R1 plus R2. That's shown here. So we have now here R1 plus R2 plus R1, and we have here R1 plus R2 minus R1. Now I lose here R1 here, so I only have here R2. That's shown here. I have here 2 times R1 plus R2. Now again, I can divide out the R2 here, so I have this expression. You see here now the expression for the oscillation period, given by 2 times the RC and times the ln of 2 times R1 over R2 plus 1. So the oscillation frequency, which is then 1 over this oscillation period, is then given by 1 over the expression here. Now there are some cases where you see the circuit where the R1 and R2 are equal to each other. That is for convenience done, and if for easy design, that can be, of course, if you do R1 is equal to R2, this expression will change to this expression, which is maybe what you encounter in the, on internet or maybe some other books. So this is the actual formula for not the special case for any other ratio R1 and R2, but this is for the special case where you have the R1 is equal to R2, where you see now here 1 over 2 RC ln 3. And this is now the expression which you can use if you have two resistors equal to each other here. Okay, now in this case, it is an important note that the duty cycle is always 50% for this circuit. It doesn't matter what you do with these resistors and capacitors, so you will stay the duty cycle as 50%. Okay, let's see now our design problem. So we have again now this square-wave oscillator circuit, same configuration. We'd like to design for an oscillation frequency of 1 kHz. The power supply for our op-amp is given as plus and a minus 15 volts, and we already picked for our R1, R2 these two values, 2 kilo ohm and 3 kilo ohm. So these are given. So we'll only need to calculate the resistor here and the capacitor for our part here. So let's see our solutions. In our case, we take for the OP1 the operational amplifier TL081. Now looking at the datasheet, the output limits are approximately 1.5 volt lower than the maximum and the minimum value. So we actually see here that the 13.5 volt is what we maximum can get, and the minimum is not this minus 15, but in this case minus 13.5. It can be maybe a little bit larger, a little bit smaller, depending on your operation amplifier circuit and a model, and of course the components around it. But this is what we expect to be, and not 15 and minus 15. So again, our formula for our oscillation frequency, this is then 1 over this oscillation period again. Now since you know the R1 and R2, we can substitute it in here, but we don't know what RC is, so R times C. So we can say this is then 1000, so 10 to the power 3, 1 over this complete thing. Again, only unknowns are 2, R and C. So we have here this RC as the ratio will be then this 1 over 1000 will be then here, place 2 times 1000, and then this same expression of ln. Now this will result here of 590 microsecond. Now we can now set, since we need two unknowns, we have two unknowns, we need to find something that, for practical purposes, it's always handy to select your capacitor. So in this case I will select 100 nanofarads, and then I can calculate the resistor by doing RC is equal to 550 microseconds. That will be then, R will be then 500 microseconds over the capacitor I have chosen here. That will be then, this will be then 5.9 kilo ohms. Okay, this is now the value I use here as a resistor, and the capacitor I have selected here, which is 100 nanofarads. So we have now all the component values here. So let's go now to the simulation results. And first, the simulation circuit. You see here the operational amplifier. We have chosen TL081. The type is in this case C. We have the two power supplies, C plus and a minus 15. The R2 and R1 here. And there is also the capacitor and the resistor there. I have also two nodes, so we will see in the display also in our graph the two waveforms, the capacitor voltage and the output voltage. There is also this pulse waveform which is required in our simulation. So in real time you don't need it, but in order to get the start the oscillation, you need some small pulse here to get it going, and then it will start. In the real time you will always have some noise, something that will get the circuit going by itself. So this is necessary in the simulator. So how does the plot look like? We have now here this red curve, which is charging, discharging, charging, discharging, charging, discharging of the capacitor and the resistor circuit, or this RC circuit. You see in the first case it's actually in a transient, and then going in now in a steady state condition. This also counts for the blue one. Blue one is the output. You see here that is not really 13.5, definitely not 15, but it is 13.2 and minus 13.2. So we already said that we never reach this 15 and minus 15 because we use the actual op-amp model, but we have 13.2, which is close to 13.5 I have found or estimated from the op-amp datasheet. What we also see here is the V max and V minimum. Again, this is a little bit different as said before, and we have also two labels here what we can use to calculate the period, oscillation period. So we can say this is the beginning at this voltage, and now at some time again I reach this maximum of this red curve at this one. So the time here, the difference is then at 0.99 milliseconds. What does it mean actually for this circuit? So what is now the oscillation here? The oscillation frequency can be calculated using this period. So we can say the oscillation frequency is 1 over this period, which is then 1010 Hertz. So it is not 1 kilohertz or 1000 Hertz, it's 1010 Hertz. So the error is, if you calculate that, it will be 1%. So that is perfectly fine for most practical purposes. If you want really exactly or very close to 1 kilohertz, you can change the circuit parameters here, the resistors or the capacitor or whatever, to get to this 1 kilohertz closer. Now, what you also see here, that's actually fine for most practical purposes, as said before. Now the beta, which is a ratio here, the feedback ratio, is R1 over R1 plus R2. In our case, it is 2000 over 2000 plus 3000, which is then 2 over 5, which is then 0.4. Is this correct? Let's see that. Now, the lower threshold is then beta times V minimum. And we said V minimum in our case, we estimated it was done minus 13.5, but in this case it was minus 13.2. So if you calculate that by doing this beta times this V minimum, you get here minus 5.28. Which is, if you look at this minimum values, it is minus 5.22 and minus 5.23, which is very close to this value actually. And looking also to the threshold high, which is then beta times V max, which is then 2 over 5 times this maximum value, which is then here given, or that one, which is here in our calculation 5.28 volts, and this is now 5.25 or 23, depending on the location where you measure it. So it is again very close to the simulated results here. So it is also perfectly fine. Alright, we have discussed the Square-Wave Oscillator circuit. First we discussed the principle. We have also discussed the hysteresis using the Schmitt trigger circuit by positive feedback, and we created using the RC circuit our Square-Wave Oscillator. And then for this design example, we have calculated the required component values and checked that using this simulation here, and we have found that our oscillation frequency is very close to what we require to have. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.